Okay, um, let's see here. So last time we worked on this example, and so we had that all points on a line. So we had all points on the line, but it was all derived through vectors, right? So points on the line were rewritten as vectors in standard position. So this represented like all points on the line, and then we had for the given point on the line. And to get all points on the line, we started at that given point and we added all scalar multiples of a vector in the same direction as the line. So you can go back and watch that animation. It's a really helpful animation to see how this works. But basically putting all scalar multiples of a direction vector starting at a point on the line then gives all the other points on the line. And so this is saying write the equation of a line that's parallel to L. So this is if this is L, write the equation of a line as parallel and through this point. Okay, so what do we need to write the equation of a line? We need the point on the line and the parallel vector, which is the direction vector. All right, so if we can find a point on the line and a vector parallel to the line, i.e. the direction vector, we can write this line. So what about a point on the line? Do we have it?
Yeah, we do. That's
the given point, right? 5, 2, -1. And then we need a direction vector. So we're given that this line is parallel to this line. So do we have a direction vector for the new line?
It's the same as the one for L.
Exactly. Vectors are mobile, right? So if it's a vector parallel to this line, will also be parallel to this line because the lines are parallel, right? So I can just use the same vector. Okay, or what? I could use any point also, so I don't have any other points immediately on this new line. So I'll just use that same point. But I could use, as a side conversation, I can use any point on the line. If I had other points on the line, those would be valid too. But I could use any scalar multiple of this, right? Why could I use any scalar multiple? Because any scalar multiple of a vector is parallel to that vector. And that's all we need for a direction vector is any vector that's parallel to our line. And so, for instance, I could do like 6, -12, -6. So that would be another valid way to write this line. Why? Because this is also parallel to our line because it's a scalar multiple of this one. But when you're writing the equation of the line,
sorry, the z value would be positive though, right?
Nope.
For the -6, would it not be positive?
So if I do -6, then it would be positive, negative, negative.
Oh, you multiplied, my bad.
Yeah, you're good. That's right. Okay, so is this a point on our new line? Could I use the 3, -3, 2? Well, I mean, only if. So what about is this point? Let's ask this question first. Is this point on this line? How would we figure that out? How do we determine whether this point is on this line or not?
Find a value of t.
Right. There would have to be a single value of t that this vector addition would generate 5, 2, -1. So we can figure out what t gives an x value of 5. So basically 3 plus t times -1 would have to be 5. And that means t would be
-2.
-2. So does -2 also give y coordinate of 2 and z coordinate of -1? So just try y. So y would be -3 plus -2 now. T times 2 is -7 is not 2. Okay? So this point is not on this line. We have this line, and then we have a point that's off that line. Okay, so here's our original line. It goes through the point 3, -3, 2. Has direction vector -1, 2, 1. And then this point, 5, 2, -1, is a different point. It's not on the line. And then in this problem, we came along and we said, okay, we want to write the equation of a line that's parallel to the first one and goes through that new point, 5, 2, -1. So we found it, right? So then the question was, could we have used 3, -3, 2 to write the equation of this new line? Yes or no? No, because it's not on the line, right? So it can't be on the line. Since 5, 2, -1 wasn't on this line, it's making a new line, then all these points, none of these points on this new line could be 3, -3, 2. So that would not be valid. You could not take the 3, -3, 2 to be a point on this line. The person who asked that, does that make sense?
Yeah, I was thinking of the drawing wrong.
Okay, does that help then, that drawing? Okay, very good. All right, questions on this example?
Professor?
Yeah.
It asked about for part 2 when at what does the line intersect the YZ plane? How do we exactly do
So
that?
what is that? What is the YZ plane? What does that mean on the YZ plane? What do you know mathematically? What do you know?
X = 0.
Right. So what do we need? For x = 0, then we need to figure out the t value that would give x = 0. So if you have the t value that gives x = 0, that's the t value that gives the point on the YZ plane. Does that make sense? Does that answer it?
Yes, thank you.
Sure. Okay. Other questions about about lines here?
Wait, Professor?
Yeah.
If you wanted to figure out if the lines are intersecting, could you just set their parametric equations equal to each other?
Yeah, so you're you're kind of assuming, so you're asking about this question now?
Yeah.
Yeah, so you're going to say, okay, we're going to try to make the x's equal and the y's equal and see what t and s I would need to do that. And if that t and s then makes the z's equal, then you'd have a intersection point.
Oh, okay. Got it. Thank you.
Sure.
And Professor, this might be different. For the test, are we going to be going all the way to 10.9, or is it just because it's next week, right?
Yeah, we're gonna need Wednesday's class to finish up test material. We're like, let's see. Yeah, we need. It depends. It depends on. There may be a little bit of material on Wednesday that would be on the test. Depends how far we get Friday.
Thank you.
Sure. Okay. Other questions?
Can I ask a question real quick?
Sure thing.
Why did, at the bottom of the screen, why did you multiply that direction vector by -6?
To show you,
just like an
example of another equation that gets you the same line.
Okay.
So I was just saying, look, this doesn't have to be -1, 2, 1. It's the natural choice. It's the least amount of work. But any vector parallel to this one is a valid direction vector for a line. So I gave an example.
Okay. That makes sense. Thank you.
Sure. Other questions? Okay, so let's talk about planes. So we talked about lines in space. So what about planes in space? So a plane is like a linear surface. It's like a flat surface. So by surface, now we mean it has 2 dimensions, right? A line really just has 1 dimension. You go backwards or forwards, and that's like positive or negative, but it's like a 1-dimensional figure. Flat linear surface. A plane, a surface, is like a 2-dimensional figure, right? So you can go in 2 different directions. Okay. So in order to write the equation of a plane, it's similar. We need 2 things. We need a point on the plane, or so let's say we need the kind of location. I should say this. Let's do this. We need the location of the plane, and that location will be determined by a point. As soon as you have a point, it kind of locks down its location, and then we need orientation of the plane. And so the question is, what thing gets us the orientation? By orientation, I mean kind of like the slant or the angle. Orientation is really the best word, but this has a slant or an orientation relative to the axes and the coordinate planes. So what kind of thing would we need that would lock down the orientation or the slant or the angle of the plane? Okay?
A vector.
Okay, so a vector, right. Okay, so let's talk about that. Good. So what about a vector that's parallel to the plane? So here I'm showing a vector that's parallel, or we could put it in the plane. If we had a vector and we said this vector is parallel to our plane, would that determine the slant or the angle or the orientation of a distinct plane?
Not necessarily, right?
Okay, why not?
Because a plane is composed of 2 axes.
Okay, so how is it that this parallel vector would not kind of uniquely determine this plane?
Because you could rotate the plane around that line.
Right, exactly. Do you see that? The rest of you? So if we think of that vector as an axis, and now think of grabbing this yellow plane and giving it a spin around that axis, all the planes that you would get, all infinitely many planes that you would get as you spun it around, they would all be parallel to this vector. So a parallel vector is not going to do it. It's not going to lock down a particular orientation in space.
You need a normal vector.
All right, what about an orthogonal vector, he said? Does that work? So let's take a look at that. So an orthogonal vector to this plane looks like this. So is there more than one orientation that is orthogonal to this vector, or does this orthogonal vector lock down the orientation of the plane?
It does not, because you could shift the plane up and down that vector.
Okay, good. So right, there are other planes. I can draw how well I'll do here. I could draw another plane like back further in the x direction, right? And it would have the same. So now, we moved it, but is the orientation the same or different?
Different. Both.
So orientation is just a matter of how it's slanted, its angle that it forms with the different coordinate planes or axes.
I mean, technically, you could rotate it, but you're not changing the overall slant of the plane.
Yeah, so you could rotate it this way.
But that doesn't change
But
anything.
does that change the set of points that you get?
No.
It's the same set of points, right? It's the same plane. All the points are just crashing into each other. So what do we think? Orthogonal vector, does it do it? Does it lock down kind of how this plane is angled to the axes and coordinate planes? Even though there's many planes that have that orthogonal vector, do they all have the same kind of orientation, same slant?
Yep, all the planes are parallel to each other.
Yeah,
right?
they're all parallel to each other, so they all have the same orientation. So this does it. You can't as soon as you try to wobble this, like wobble it and change its slant, change its orientation, it's no longer orthogonal to this vector. Is that making sense to everybody? So what do we want? So the location. So then this would just be a matter of moving. That would just be a matter of a different point on the plane, right? So a point on this plane versus a point on this plane. So the point gives us the location, and the orientation we can get from orthogonal vector. And another name for that is normal. So now we have three terms that mean the same thing: orthogonal, normal, perpendicular. Orthogonal, normal, perpendicular all have the same meaning for us. And perpendicular is kind of just reserved for lower dimensions when it makes a right angle, right? So in higher dimensions, you don't really have right angles, but you still have this concept of orthogonality. Okay, so let's see how the equation of a plane comes to be here. Now that we know how to orient it using an orthogonal vector and how to like fix its location using a point. Okay, so here we go. So first, I'm going to write that point in the plane. I'm going to show that point as a vector in standard position, much like we did with the line. So this vector is x naught, y naught, z naught, and it's pointing right at our given point. So this is our given point, x naught, y naught, z naught. And then I'm going to take my orientation vector, my orthogonal vector, and put its tail on that point. Okay? And we're going to call that vector A, B, C. Now, you got to be careful, right? Because what was A, B, C for a line? How did it relate to the line?
Was the direction by the line of the line?
The direction of the line, which is what? Orthogonal or parallel?
Parallel.
Parallel. Okay, so you got to keep your wits about you here. When you're dealing with this generic version of, the orientation ABC, well, for a line, that's parallel to our line in the equation. But we use the same symbols to be perpendicular to the plane. So make sure you, in a given situation, make sure you have that straight. You know what you're using, okay? All right, so we want to write now, we've got our given point. We're putting the orthogonal vector, its tail, on the given point. And we want to write. So now this represents just all points on the plane, this red vector. And so that would be what? All points would be x, y, and z as a vector, right? So these two vectors in standard position, they're pointing at locations on the plane. And then we put the tail of our orthogonal vector on the given point. And so what we're interested in is then all points on the plane, right? So this is our mobile vector that's going to give us all points on the plane. Okay, so we know we're going to use orthogonality, right? The whole point that this vector is orthogonal to plane. So what was our big mathematical conclusion with orthogonality, or the big association, the mathematical dot? What's that?
And it's going to equal 0.
Which one? Which?
The dot product of your normal vector and the point. The difference between x, y, and z and the point.
All right, so the equation of the plane then is going to be based on the dot product equaling 0. Because the whole point is that this vector is orthogonal to the plane. So the dot product of ABC and what? That's the question. ABC and what vector is going to have a dot product of 0? Is it going to be ABC and x naught, y naught, z naught? Are those orthogonal?
Could it be any point on the plane?
It has to be a vector that lies in the plane.
Would it be x, y, z minus x naught, y naught, z naught?
Okay, some of you are getting it, right? So someone said, it's going to be a vector lying in the plane or parallel to the plane. Okay, do either of these vectors lie in the plane or are parallel to the plane?
No.
No, but we can make one out of these, right? So how do we make a vector that's parallel to or lies in the plane out of these two? We've got 2 points on the plane, right?
That's an attract on.
X minus x now.
Yeah.
Y minus y now. Z minus z now.
Very good. Lots of you are seeing it. We want to do this vector right here, which is what? The vector from our fixed point to every other point in the plane. It's the vector from our fixed point, or given point, to every other point in the plane. And that will always be parallel to the plane. So it will always be what? Orthogonal to the ABC vector. So I have that here. It's that one. So and that's going to represent every point in the plane. That pink vector is always parallel to lying in the plane. Therefore, it's always orthogonal to this vector. And that pink vector is what? We got them tail to tail, so final minus initial. X, and so some of you are picking up on this. X minus x naught, y minus y naught, z minus z naught. So that's in the plane, parallel to the plane, orthogonal to the plane, dot product is 0. Does it make sense? So we got the difference of these two vectors and then the dot product, and that derives our equation of the plane. And so we're going to actually do the computation here. That's our dot product, right? Multiply x's, multiply y's, multiply z's, and add. And so this is going to be, if we want to write the equation of a new plane, that's the formula used. What do we need? We need a point that locks down the location of the plane. We need an orthogonal vector that locks down the slant or the orientation in space. And that's our A. So there's our orthogonal vector ABC. There's our given point x naught, y naught, z naught. How are we doing? Any questions? Okay, so what we can do now is we can keep doing some algebra on this. So I'm going to distribute the A, B, and C. So I'm going to get AX okay, and then I want to hold on to these variable expressions on the left side and move all these constants, right? So these are all values. So there's constants. I'm going to move them over to the right. So it'll be plus A. So what is this? Is this a variable or a constant? Over here
Constant.
Yeah, those are all numbers, right? This is product. And so that's just really just a number. Some number. And so since it's just some number, I'll just call it d. And so here's another equation of the plane, and then this is, more compact, but it kind of, at first glance, it tells you less, right? What's the only thing you can see? Just what's the only thing staring you in the face here in this form of the equation?
It's x, y, z coordinates and its radius, so it would seem like it's a sphere.
No, sphere would be the x minus center squared, y minus center squared, z minus center squared. So it's much different than a sphere because you don't have any squares. But
it kind of looks like the equation of a line, but like scaled up to 3 dimensions.
Okay, yeah, it's linear, right? We said it's a linear surface, a linear, three-dimensional surface. But what my question was, I'll ask the question when I put an example up. But when you have problems, so planes are often given this way. Planes often given in this form. So when you're writing an equation of a new plane, this is going to be most convenient, okay? You're going to plug in your point and your orthogonal vector. But when you're working problems and they say such and such plane and they're giving it to you, well, they'll often give it to you in this form. For example, 3x minus 6y plus z equals 2. Or say 12. So looking at that, what's the one thing you know without doing any work? What do you know right away about this plane?
The orientation vector.
Yeah, what is it?
3, -6, 1.
So 3, -6, 1. Is that a point in the plane, or what is it?
It's the normal vector to the plane.
Yeah, that's the norm. That's the orthogonal vector. So you don't have immediately you don't have a point that you're staring at here. There's no point in the plane that's staring you in the face. What is staring you in the face is the normal vector in this form. Okay, but we're gonna need points, right? So this is not just the name or the label for a plane. This is mathematically equivalent to the plane. How is it mathematically equivalent to the plane?
Any set of x, y, and z values that satisfy that equation lie on that plane.
Well said. Did you hear that? That was awesome, right? Any ordered triple that makes this equation true is a point on the plane. Any ordered triple that does not make this equation true is not on the plane, right? So that's how mathematically it's equivalent to the plane. It's not just, here's a plane and this is its name, right? This is just what it's called. No, this is the math. This is the math that gives you all the points. Any point that satisfies that equation is a point on the plane. So how are we going to find? I want to find some points on this plane. That means finding ordered triples that make that true. So what could be a strategy to find an ordered triple that makes that equation true?
You could set each component equal to 12 and solve for the x, the y, and the z.
Okay, so for instance, if I set this 3x equal to 12, is that what you're saying?
Yes.
We get x equals 4. So what point on the plane would that be telling me?
That
4, 0, 0.
R0.
So
I thought it would just be the 4 and then
4, 2, 12, 4, -2, 12?
yes.
Well, what would happen then is you would get 12 plus 12 plus 12. Does that equal 12?
No, the 4 when y and z are equal to 0.
Yeah, so if x equals 4 gives 12, well, we've already taken care of the 12. So what would y and z need to be?
0.
Does that make sense? The person who originally was talking about that?
Yeah, that does.
Yeah, good. Okay, so Yeah, but I mean, we kind of figured it out. You guys kind of figured it out yourself. That's good. So 4, 0, 0.
Did you also do 4, 2, 12?
Yeah, so, right. So here's the thing about this. This equation has 3 variables. So what it means is there's something called degrees of freedom. This has 2 degrees of freedom, meaning you're free to pick any 2 variables to be any 2 values you want. Then the freedom is over, right? You've used up your 2 degrees of freedom. Then the third variable is fixed once you pick your first 2. So like for this one, we picked y and z to be 0. Once you pick y and z to be 0, x is determined. It has to be 4. Make sense? Okay, and then so what about you could pick x and y to be 0? Z would be? You could pick x and z to be 0.
-4.
-2.
-2.
Oh, sorry.
That's okay. And very quickly, you can generate lots of points. So now, those were kind of the easiest ones. So now you could do 1, 0. X is 1, y is 0. So then we'd have 3x plus z equals 12. Or 3. 3 plus z equals 12. So z would be? 9. So 2 degrees of freedom, a wonderful thing, right? You can pick, for any 2 variables, you're free. You can pick them to be any numbers you want. But then once you do that, the freedom is over. The other variable, its value is determined, and you have to solve for it. So we can choose 1 and 1 for y and z, and then what would x have to be? So 1 minus 6, so minus 5. That's 7/3. Check my math. So how do we check the math? Put it in and see if it makes it right. So that would be 7 minus 6 plus 1. Not right. What did I do wrong? So I want to do y and z are 1. Let's try it again.
It's plus 5.
Right, so this is minus 5.
And then you add 5.
You 17 thirds.
17/3. There we go. Okay, so does finding, given a plane, generating lots of points, does that make sense? Does that make sense how you do that? What is special about these 3 points on the plane?
Lie on the 3 axes.
Right, these are our intercepts. These are our axes, intercepts. When you set 2 variables equal to 0, now you're talking about on an axis, right? On the other axis. So these are the 3 points where that plane intersects the 3 axes, x-axis, z-axis, y-axis.
Professor?
Yes, please.
Does the process change at all for finding points if the orthogonal vector is one of the axes? Like it's in one of the cardinal directions?
It just makes it for a really easy plane, right? If your orthogonal vector is, say, the negative x-axis, well, then you have to have a vertical plane like that. So, I mean, the plane is just, x equals the number, right?
Oh wow, that makes it really easy.
So so then it's just all points with an x coordinate of 4. If your orthogonal vector is, say, -2, 0, 0, then you have a plane that is orthogonal to the x-axis. So that has to be a vertical plane parallel to the y-z plane. So that just means that all your x values are the same. Okay, other questions? All right, let's look at some examples of some plane examples. Start with some easy ones. All right, so a plane has a normal vector of 2, negative 2, 1, and contains the point 1, negative 1, 0. So first of all, write the equation of that plane. Most basic skill. Given the normal vector and the point, what's the equation of that plane? Somebody knew. No volunteers?
Oh, I could try.
Go for it.
Negative 2x, 2x minus 2y plus z.
Yeah, but then you're not going to know what d is, right? So you're trying to use this one. So I don't recommend, if you're writing a new plane, I don't recommend doing this one.
Okay.
So I recommend using this one to write a new plane, unless you want to use that formula for d. You could do that. But I recommend, if you're writing a new plane, use this.
All right. So 2 times x minus 1 plus negative 2 times y plus 1 plus, just in parentheses, z. Oh, that's it. All right. Equals 0.
Right. There you go. So there's that plane. All right. Now we want, and we could multiply that out and make it look like this. That'd be fine. But this is totally valid the way it is. All right. How about the equation of the plane parallel to this one, but through this new point? Okay. So I'm writing a new plane now. This one was P1. And I want to write a plane that's parallel to P1 and through this point. Somebody knew. How will I do that?
You try.
So again, we need two things. We need a point on the plane, and we need our orthogonal vector. So do we have both of those?
Yes. Yes, we do. Yes.
If the planes are parallel, then they have the same normal vector.
Right. Exactly. If they're parallel planes, their orthogonal or normal vectors will be the same. So we can just use the same normal vector as for the first one. And then we have the point. So what will it be? 2 times x plus 5 plus
negative 2
times y
minus 2
minus 2 plus 1 then minus 5 negative 3.
Did I write it down right?
Yeah. That's a new equation.
Right. And so this is going to have the same, when you look at these two plane equations, they'll have the same, if you do it in this form, they'll have the same left side, because they're going to have the same A, B, C, but then they'll have a different D, right? They'll have a different D, meaning parallel planes, but not the same plane. Okay? How about writing the equation of the line that's normal to this plane and through this point?
Does D come from moving the x0, y0, and z0?
A times, yes.
Okay.
That's this. That ends up being this. when you move it over. So you go back and watch the video on the previous screen. We derived that, and that's, yeah, it's when you multiply that and you move those three terms over. And we just said that's a number, and we called it D. All right. So what about the equation of a line that's normal to this first plane and through the point -1, -4, 0? So what do I need to write the equation of a line? I need a point and parallel vector or direction vector.
Which we're already given the direction vector, correct?
So how is it that we have the direction vector of the line? If this line is orthogonal to the plane, so here's my orthogonal vector to that plane. I'm writing a line orthogonal to that plane through the point, what?
2 points and their subtractions.
-1, -4, 0. Here's P1. So my point is given for the line. My orthogonal vector, sorry, my parallel vector. So how can I get the parallel vector or the direction vector for this line? If it's orthogonal to the plane. Yeah, if it's orthogonal to the plane, then the line is parallel to the plane's orthogonal vector, right? These are both orthogonal to the plane, so they are parallel. So I'm going to get my point, -1, -4, 0, plus t times what?
2, -2, 1.
2, -2, 1. Right? I'm using the orthogonal vector for the plane to be the parallel vector for the line because the line is orthogonal to the plane. So we can use that for its direction. So that's the answer to number 2.
Professor, could you also find the orthogonal vector just by multiplying them out and, you know, adding them up and making sure they're 0?
Which? I'm not sure what you mean.
The vectors, like for example, it asks us to find the orthogonal line to point P1. Couldn't you do that by taking the points and just multiplying them out and then seeing if it equals 0? Like x1, x2, for example, then you're multiplying out and then adding it together, if that makes any sense.
I'm not sure what you just keep saying points. You're going to multiply the points together, so I'm not sure. Maybe ask me after the quiz.
Okay.
Yeah, because I'm not really following what you're saying.
Why did you use the 2, -2, 1?
Because I need a direction of this line. How am I going to get the direction of this line? Well, the line is orthogonal to the plane. So I need a vector that's orthogonal to the plane. What vector is orthogonal to the plane?
Normal vector.
The normal vector for the plane. See? Here it is. And so it's my direction of my line if the line is orthogonal to the plane. Okay, so I'm gonna open the quiz. I'm gonna publish the quiz for you to take the quiz. The question 3, we didn't really talk about it, but I think many of you can get it. It'll be like a bonus question, but definitely questions 1 and 2 are things we talked about. So let me open that up. And then remember, you have the written homework due tomorrow night, and you have the next web work I'll push back to next Tuesday night, but definitely get going on it. You have lots and lots of information to start working on the next web work. And then I'll stick around after the quiz for questions.
What number quiz are we on?
05. It's not open. I have to go publish it.